Hey guys, tonight we dive into something that might seem abstract and mind-bending at first, but trust me, it's deeply fascinating. We're exploring nebulae, star nurseries in the galaxy. Yes, you heard that right. Forget any idea you might have that outer space is just an empty void, or that those colorful clouds in sci-fi movies are just pretty backdrops for starships. We're going to peek behind the curtain of nebulae and star formation, all the way into the incredible processes and hidden wonders inside these cosmic clouds that rarely make it into textbooks in a way that truly makes sense. How can a cold, dark cloud of gas give birth to a brilliant star? Why do these nebulae glow in so many breathtaking colors and shapes? What would it be like to actually travel through one of these stellar nurseries? And could our own sun have come from such a place? And what do these gigantic clouds have to do with the story of life itself? Brace yourself for some mind-expanding and wonderfully cosmic details. This won't be a dry lecture, but it will be fascinating. Before we dive into this scientific journey, take a moment to get comfortable. Dim the lights, maybe turn on a gentle fan or some soft background sounds. And if you enjoy these late-night science explorations, consider liking this video and subscribing to the channel. It really helps me continue these journeys into the beautiful world of science. Feel free to let me know in the comments where you're listening from and what time it is for you right now. I love seeing the global community gathered for these stories. Now take a deep breath and relax. Let's ease into tonight's journey together, into the incredible world of nebulae, and uncover the beautiful details of how these star nurseries actually work. Imagine for a moment you're standing under a clear night sky, gazing up at the stars. Among the countless twinkling lights, you notice a faint, fuzzy patch in the constellation, Orion, just below his famous belt. Through binoculars or a small telescope, that fuzzy spot blossoms into a gentle glow. That is the Orion Nebula, one of the nearest stellar nurseries to Earth. It's not a single star at all, but a sprawling cloud of gas and dust about 1,300 light-years away, where new stars are being born as we speak. This glowing patch has been noticed by skywatchers for centuries, appearing as a tiny, misty star to the naked eye. In fact, there are hints that even ancient cultures recognized something curious about it. The Mayans of Central America, for example, told of a cosmic hearth in the sky, 3 bright stars forming a triangle with a smoky patch at the center, which some believe correspond to Orion's belt, and the Orion Nebula as the embers of creation. Without knowing its scientific reality, they metaphorically linked that fuzzy glow to the idea of cosmic creation. Yet in reality, the Orion Nebula spans 20 light-years across, an enormous cosmic cloud that could fit our entire solar system inside it many, many times over. To give you a sense of scale, 1 light-year is about 9.5 trillion kilometers, almost 6 trillion miles. So a nebula like Orion, at roughly 20 light-years wide, measures on the order of 190 trillion kilometers across. That's a number almost impossible to imagine. If you hopped in a hypothetical spaceship that could travel at the speed of a commercial airliner, it would take you millions of years to cross that distance. Even a beam of light, the fastest thing there is, needs 20 years to go from one end of the Orion Nebula to the other. These dimensions are mind-boggling, but they show just how vast nebulae are, even though they might look like small smudges from our perspective on Earth. So what exactly is a nebula? In simple terms, a nebula is a giant cloud of dust and gas in space. The word nebula even comes from the Latin word for cloud, and that's a pretty good mental image. A nebula is like a cloud in the cosmic sense, except far larger and much more diffuse than any cloud you see in Earth's sky. Nebulae, that's the plural of nebula, can stretch across dozens or even hundreds of light years. They are made mostly of hydrogen gas, with a sprinkling of other gases like helium, and a dusting of heavier elements such as carbon, oxygen, nitrogen, and tiny solid grains we call cosmic dust. These ingredients are spread out incredibly thin, far thinner than even the emptiest air you could ever breathe. If you were inside a nebula, each cubic centimeter of space might contain just a few hundred or thousand atoms, whereas the air you're breathing has trillions upon trillions of atoms in the same volume. Yet over these vast volumes of space, that thin soup of gas and dust adds up to a lot of material. And under the right conditions, something truly magical happens. New stars begin to take shape inside. Nebulae aren't all alike. They come in a variety of forms and personalities. Some are the picturesque, colorful backdrops you might have seen in astronomy books or on wallpaper images. They glow in shades of pink, red, blue, or green, sculpted into fantastic shapes. Others are dark and eerie, visible only because they block the light of stars behind them, appearing as cosmic silhouettes against the starry field. Astronomers classify nebulae by these appearances. There are emission nebulae, which shine with their own light. They are lit from within by young, hot stars that energize the gas and make it glow, somewhat like a neon sign or a fluorescent lamp glowing when excited by electricity. Then there are reflection nebulae, which don't emit significant visible light on their own, but gently reflect the light of nearby stars, often in a soft blue hue. This is similar to how dust in Earth's atmosphere scatters sunlight and makes the daytime sky blue. In space, microscopic dust grains scatter starlight. And then there are dark nebulae, thick clouds of dust that don't emit or reflect much visible light at all. Instead, they loom as dark patches, hiding whatever lies behind them. An example of a dark nebula is the famous Horsehead Nebula, a striking silhouette shaped like a horse's head, set against a backdrop of glowing gas. In that case, the horsehead shape is a dense lump of opaque dust and gas in front of a brighter region, casting a shadow. In fact, some of the prominent dark patches you can see with your naked eyes on a clear Milky Way night, like the Great Rift that splits the Milky Way lengthwise, or the Coal Sack Nebula near the Southern Cross in the southern sky, are caused by such dark nebulae blocking the glow of countless distant stars. Early skywatchers saw those voids and gave them imaginative names: the coal sack, the dark horse, even an emu in some Aboriginal Australian traditions, not realizing they were looking at enormous clouds of interstellar dust in our line of sight. All these different appearances are just variations on the same theme: cosmic clouds of gas and dust, behaving a little differently depending on their environment. Some nebulae are lit up by stars and proclaim themselves in radiant colors. Others hide in shadow form. And intriguingly, many nebulae have dual identities over time. The same cloud that starts as a dark nebula might become an emission nebula once stars ignite inside it, turning from invisible to luminous. In the grand story of the cosmos, nebulae are both the canvases and the artists. They are shaped by starlight, even as they are giving birth to starlight. Now, let's drift deeper into one of these star nurseries and see how stars actually come to life inside a nebula. It all starts with a quiet, cold cloud of gas and dust floating in the darkness of space. For ages, nothing much might happen. The cloud just hangs there, minding its own business. But then, perhaps a gentle nudge comes along. Maybe a shock wave from a distant supernova explosion rolls through, or two galaxies brush past each other and disturb the gas, or even just the random ebb and flow of the cloud causes a part of it to become a bit denser. Whatever the trigger, one section of the nebula begins to gather more material, its gravity subtly pulling in gas from around it. This is the very beginning of a new star. Let's zoom in on that little patch of cloud and imagine we could watch what happens to it over time. At first, it's just a slightly denser blob in a vast sea of gas, perhaps a bit cooler than its surroundings and rich in dust. It's so tenuous that if you were floating inside it, you'd still think you were in a near vacuum. But slowly, imperceptibly, that blob is getting denser. The outside push, maybe from that supernova shock or another disturbance, has given gravity the upper hand in this region. Now gravity is drawing more and more gas inward. If we could accelerate time, we'd see gas streaming, ever so gently, toward that blob's center, like water swirling down a drain in extreme slow motion. As the gas accumulates, the blob's core starts to pressurize and warm up. Imagine centuries passing as this happens. The temperature creeps up from just a few degrees above absolute zero, rising into the tens of kelvins, then hundreds. That might still seem cold by human standards, but in space, it's a sign of something happening. The ball of gas is thickening. After some millennia, it becomes opaque to its own radiation. The heat can't escape as easily now, so the temperature climbs faster. Our little clump has become a kind of embryo star, a protostar, still gathering mass from the infalling gas. It's cocooned inside a dusty shroud, so from the outside, it's invisible in normal light. If you were nearby, safely in a spaceship of course, you wouldn't see a bright star yet, just a deeper darkness in the cloud. But inside, the protostar is getting denser and hotter. It starts to glow faintly in infrared, like a warm ember buried in ashes. During this protostar phase, especially for stars around the sun's mass or smaller, the object often goes through what's known as a T Tauri stage. It's a tumultuous toddler period for a star. The protostar is vigorously churning and contracting, generating strong magnetic fields that drive impressive stellar winds and flares. Such infant stars sometimes shoot out twin jets from their poles and can flicker in brightness as they gobble up material in fits and starts. Our own sun likely went through this kind of fiery childhood. If we could watch a T Tauri star up close, we'd see a star that hasn't yet settled, still cocooned in dust and prone to outbursts. Not yet the steady beacon it will eventually become. Because nature likes to conserve momentum, as the gas cloud contracts, it also starts to spin, a bit like a figure skater pulling in her arms and spinning faster. What began as a slow, lazy rotation of the whole cloud now turns into a faster whirlpool as the gas falls toward the center. The result is that the collapsing clump flattens into a disk around the growing protostar. Picture a cosmic pancake or a frisbee of gas and dust encircling a central ball of hot gas. This is the protostellar accretion disk, and it's a bustling construction zone. In that disk, gas and dust are not just feeding the baby star, they are also beginning to clump together to form planets, moons, asteroids, and comets. In other words, alongside the birth of a star, the seeds of a future solar system are taking shape. It's a beautiful parallel process. At the same time the star is coming to life, a family of planets might be assembling around it in the disk. Let's allow that image to sink in for a moment. A star in the making, swaddled in a spinning disk of raw material, hidden in the depths of a nebula. Millions of such scenarios are playing out across our galaxy, slowly and silently, over tens of thousands to millions of years. If we could speed up time and watch, we'd see these little cocoons flicker on like fireflies in the night, each one a newborn star igniting. The protostar continues to gather mass from its surroundings. Eventually, when enough material has fallen in, the pressure and temperature at the center of the protostar reach a critical point. Nuclear fusion ignites. Hydrogen atoms begin to fuse into helium, releasing a tremendous amount of energy. At that moment, a star is truly born. It's as if a light bulb suddenly switches on after a long, dim glow. The new star starts to shine brilliantly, and its radiation and stellar winds, streams of charged particles blowing outward, surge into the surrounding nebula. This changes everything around it. The once hidden protostar now announces its presence dramatically. The intense light and wind from the newborn star push away the remaining cocoon of gas and dust that lingered around it. It's akin to the sun burning away morning fog, or a campfire heating the air and causing the mist to disperse. The nebula around the new star gets blown back, and often we see a kind of cavity or bubble around young stars where their energetic presence has cleared the space. In regions where many stars are born together, their combined energy can literally carve out huge hollows in the nebula, like a cavity opening in a cloud. The pillars of creation in the Eagle Nebula are a famous example of what remains when powerful young stars erode the clouds that formed them. Towering columns of gas and dust left behind, shielding littler protostars within, until those two emerge. Each pillar is roughly 4 or 5 light-years tall, about the distance from our sun to the next nearest star. These structures exist only because dense knots of gas are temporarily resisting the onslaught of radiation from a cluster of massive newborn stars nearby. Inside them, new stars are still forming, sheltered for now. The name Pillars of Creation comes from the fact that within those pillars, stars are being born. They are literally pillars of star creation amid a storm of starlight. Over time, even these pillars will be eroded away. In fact, astronomers suspect that a supernova shock may have already struck the Eagle Nebula a few thousand years ago and obliterated the pillars. We just haven't seen the aftermath yet, since the light is still en route to us across space. It's important to realize that stars usually form in batches, not solo. A single giant molecular cloud, which is the name for the large, cold nebula where stars form, can give birth to dozens or hundreds of stars in one go, like a cosmic nursery full of siblings. These sibling stars can range widely in size. Some may be huge, hot and short-lived, while others may be small, dim red dwarfs that will outlive everyone. In the Orion Nebula, for instance, there is not just one star, but an entire cluster of young stars, including a group called the Trapezium, that have recently formed together. They are like a litter of star babies born out of the same cloud. And just as siblings can be very different, so too are these stars. The biggest ones shine tens of thousands of times brighter than our sun, while the smallest may be mere fractions of the sun's mass and luminosity. Those massive newborn stars have an outsized influence on the nursery. The most massive stars, O-type or B-type stars, emit fierce ultraviolet light and drive strong stellar winds. They are essentially cosmic blowtorches. Their radiation ionizes the nebula's gas, making it glow wonderfully, but their energy also blows giant bubbles in the gas and can even halt the formation of smaller stars nearby by blasting away the material those smaller protostars were trying to accrete. In a way, the rambunctious big siblings tend to disrupt the nursery for the smaller ones. They carve fantastic shapes in the cloud, like those finger-like pillars we mentioned, or great sweeping ridges and cavities. The beauty we see in images of nebulae, those billowing forms and arches, often comes from this interplay. Stars are being born, and at the same time their energy is sculpting the surrounding gas into wondrous forms. It's a bit of cosmic irony that when the biggest, brightest stars light up, they also begin to tear apart the very cloud that created them. Over a few million years, a star-forming nebula like Orion or Carina changes dramatically. The brightest and hottest stars form first and quickly blow out or evaporate much of the remaining gas around them, essentially shutting down the nursery after they've had their turn. Star formation might continue in a few sheltered pockets for a while, but once enough stars have turned on, the nursery effectively starts to close its doors. Astronomers have found that these stellar nurseries aren't very efficient at turning gas into stars. Perhaps only a few % of the nebula's mass ends up as new stars, and the rest is driven off into space. But that's not necessarily a bad thing. It means there will be raw material left over, spread around to potentially form new clouds and stars elsewhere. When the nebula finally disperses, it leaves behind a cluster of newborn stars that have freed themselves from their birth cloud, like a group of children who have grown up and left home after the nursery lights have been turned on. These newborn stars initially stick together in a loose cluster, bound by their mutual gravity. They may orbit around each other in the cluster for tens or even hundreds of millions of years, but eventually, gravitational interactions and outside influences, like tidal forces from the galaxy, pull the cluster apart. The siblings go their separate ways, each star embarking on its own orbit around the center of the galaxy. Our own sun is thought to have been born in such a cluster about 4.6 billion years ago. Can you imagine? The sun, now solitary in our sky, likely began life with dozens or maybe hundreds of stellar siblings. As the eons passed, that family of stars gradually dispersed all across the Milky Way. Once in a while, astronomers try to identify our sun's long-lost siblings by finding stars with similar ages and chemical compositions and tracing their motions backward. It's like a cosmic genealogy project. A few candidates for the sun's sisters and brothers have been proposed, but it's challenging to know for sure after so much time and drift. Still, just knowing that our sun probably grew up in a cosmic brood gives a nice sense of context. On some level, every star you see might have had a nursery and a family at birth. There's also tantalizing evidence that a supernova from a massive sibling might have gone off near our infant solar system. Certain isotopes found in ancient meteorites, like a type of aluminum that decays in a way which indicates a nearby supernova, suggests that not long after the sun formed, an enormous star exploded in its vicinity, showering our young solar nebula with exotic elements. It's quite possible that the shockwave from that very explosion helped trigger the collapse of our sun's parental cloud in the first place, a stellar fireworks that kicked our formation into gear. If true, it means we owe our existence, in part, to the life and death of a star that was born alongside the sun, a stellar sibling that lived fast and died young, enriching our little corner of the cosmos with the heavy elements that would become, among other things, our planet and even our bodies. And here's an even deeper connection. The material that formed our sun, the Earth, and all of us originally came from previous generations of stars' remnants. The oxygen we breathe, the carbon in our cells, the calcium in our bones, the iron in our blood, those atoms were forged in older stars and scattered across space when those stars died. Nebulae are the great intermediate step in this cosmic cycle of life and death. A star lives out its life, and when it dies, it returns much of its substance back to space. For a star like the sun, That might be a gentle shedding of outer layers as a pretty planetary nebula, glowing with the star's farewell light. For bigger stars, it can be a catastrophic supernova explosion that blasts heavy elements in all directions. Either way, the result is gas and dust enriched with new elements, mixing into the galactic medium. These cast-off materials gather into nebulae, which then give birth to new stars and new planets. Our solar system was one such offspring of countless earlier generations of stars. So in a very literal sense, we are made of stardust. The gold in a ring on your finger, the silicon in the glass of your window, the iron in your blood, all were forged in some ancient star and dispersed through a nebula before they became part of us. Let that sink in for a moment. Every atom in your body heavier than hydrogen, and most of them are, has likely experienced the inside of a star and drifted across light years in a nebula before coming together to be part of you. Now, you might be wondering, what would it actually look and feel like to be inside a nebula? We've all seen those gorgeous photographs of nebulae, with colors and shapes swirling like a cosmic painting. But those images are usually captured by powerful telescopes with long exposures, or using special filters that highlight emissions our eyes can't see. If somehow you could teleport in your spaceship right into the middle of a nebula like the Orion Nebula, the reality might surprise you. First off, you likely wouldn't see the brilliant colors with your unaided eyes. Nebulae are extremely diffuse. Remember, even the densest parts are a better vacuum than anything we can make on Earth. The gas and dust is spread so thin that up close, the glow would be faint. Space would mostly still look black to your eyes, dotted with stars as always. You might notice a slight haze or an ethereal glow around the brightest stars in the region. Maybe a very subtle pinkish or greenish tinge if you were near a particularly bright patch of ionized gas. It would be a bit like being inside a very faint, foggy cloud illuminated by distant city lights at night. Except the city lights are young stars scattered around. The nebula wouldn't be overwhelmingly bright. In fact, you'd probably have to let your eyes adjust to darkness to even realize the cloud is there at all. It's as if you were floating in a vast, silent fog that only gently glows. However, if you had sensitive instruments or cameras on your ship, you could start to pull out the majestic details. Long exposure photographs from inside the nebula would reveal curtains and filaments of gas all around, glowing in reds and blues. You might see dark tendrils of dust snaking across a luminous backdrop where the nebula is denser. Imagine looking out one window of your craft and seeing a great wall of gas faintly lit by newborn stars hidden within it, and out another window, a clearer view toward the edge of the cloud where the stars shine unobscured in the black of space. The contrast would be breathtaking in its own subtle way. One thing you would definitely notice is the cluster of young stars itself. In a place like the Orion Nebula, there are multiple intense stars, like the trapezium cluster, all in a tight group. They would be so bright that, up close, they might cast eerie shadows through the nebular haze. You'd see them blazing, blue-white and brilliant, far more luminous than our sun. These stars would be the primary lighthouses making the nebula glow at all. If you were near such a star, the surrounding gas might actually become visible to you as a faintly colored mist, lit up by that star's ultraviolet rays. It would be an otherworldly sight, a starry lantern illuminating gauzy cosmic fog all around you. The experience of being inside a nebula would also be profoundly silent and surreal. Despite being called clouds, there is no whoosh of wind as there is on Earth. The gas is too thin to feel, And without a medium like air, sound doesn't carry. You would be enveloped in a nearly perfect vacuum. If you stepped outside your ship in a spacesuit, a risky move near energetic stars, but let's imagine. You wouldn't hear anything except the sound of your own breathing. The particles of the nebula are so sparse that you'd pass through them without noticing. It's mind-boggling. You're in the middle of this enormous structure that looks so dense in pictures, yet physically, you'd feel like you're in empty space. Take a moment to picture that. Drifting in the quiet heart of a stellar nursery, surrounded by a ghostly glimmer. Perhaps in the distance, you see a star being born, a knot in the cloud shining a bit brighter, with faint bipolar jets of gas streaming out from it like beams from a lighthouse. You might catch a glimpse of those jets if they collide with a clump of gas, creating a luminous splash. Astronomers call those Herbig-Haro objects, a technical name for the glowing shocks, where a baby star's outflow rams into the surrounding material. In your mind's eye, you can imagine looking at a nearby newborn star and seeing twin searchlight-like beams of energy, one on each side, piercing into the darkness of the nebula. What a light show that would be, quietly unfolding over years. So while the human eye might not see the vibrant colors without help, the sheer scale and subtle beauty of being in a nebula would be unforgettable. You would be witnessing creation in slow motion. Everywhere around you, gravity is pulling, stars are forming, and light is sculpting darkness. It's a calm yet profound scene, more peaceful glow than fireworks when viewed from within. You might feel a kind of serene awe, realizing that this gentle cradle of gas will one day disperse, sending its stellar children out into the galaxy. Speaking of our galaxy, let's zoom out now and consider the grand tapestry in which these nurseries exist. Our Milky Way galaxy is a colossal disk of stars, about 100,000 light-years across. Sprinkled throughout this disk are countless nebulae. They tend to congregate in the spiral arms of the galaxy, those swirly patterns you see in pictures of spiral galaxies. Think of the spiral arms as traffic jams of gas and stars. As the galaxy rotates, these arms are regions where gas clouds get a little more squeezed together, triggering more star formation. If we could view the Milky Way from afar, we'd see the spiral arms outlined by bright young stars and glowing nebulae, like festive lights on a celestial spiral. In fact, the very reason we see spiral arms at all is largely because of the blue light of massive young stars and the pinkish-red glow of ionized nebulae within them. The Milky Way's arms are essentially the locations of ongoing stellar nurseries. There are thousands of known star-forming regions in our galaxy, and they vary greatly in scale and activity. Some stellar nurseries are actually quite small and short-lived, forming just a few stars in relative isolation. One example is the Rho Ophiuchi cloud complex, one of the closest star-forming regions to Earth. It's only about 400 to 460 light-years away in the constellation Ophiuchus. This dark, smoke-like cloud is birthing a handful of low-mass stars, nothing like the sprawling Orion or Carina nebulae, but significant as a local nursery. In visible light, you wouldn't even know there's a star factory there. It's mostly opaque dust-blocking starlight, but infrared observations peel back the darkness and reveal dozens of infant stars swaddled in that cloud. Rho Ophiuchi shows that star formation can happen on a small, quiet scale right in our cosmic backyard, not only in the giant showpiece nebulae. On the other hand, some stellar nurseries are colossal and extravagant, birthing clusters upon clusters of stars. For example, we talked about the Orion Nebula, which is part of a larger structure called the Orion Molecular Cloud Complex. a vast collection of gas stretching across much of the Orion constellation. That whole complex is an active stellar nursery with multiple pockets of star formation. The Orion Nebula is just one particularly bright spot within it. Further along one of the spiral arms, there's the Carina Nebula in the southern sky, an even larger and more tumultuous cloud on the order of 200 plus light years across, boiling with bright young stars and carved by their power. Within Carina lies one of the most massive and temperamental stars in our galaxy, Eta Carinae. In the 1840s, this star mysteriously erupted in a colossal outburst, briefly becoming the second brightest star in the entire sky. That event, known as the Great Eruption, wasn't a full supernova, but it expelled an enormous cloud of gas and dust, forming what we now call the Homunculus Nebula, a twin-lobed bubble enveloping Eta Carinae. The star survived, but it was severely destabilized, and it remains on the brink of catastrophe. Eta Carinae is like a stellar ticking time bomb. Astronomers suspect it could explode as a true supernova any time in the next few 100,000 years, which is practically soon by stellar standards. When it finally does, it will briefly outshine all other stars in the galaxy. For now, Eta Carinae's furious winds and past eruptions have already carved out cavities in the Carina Nebula and lit up the surrounding gas in unusual ways. It's a vivid reminder that within these nurseries, some stars are leading very dramatic lives and even dying, all while new ones form around them. The Carina Nebula itself offers an incredible vista of star formation. Great pillars and mounds of gas are ablaze with starlight. NASA's James Webb Telescope recently produced an image of the so-called cosmic cliffs in Carina, a craggy-looking wall of gas that truly resembles a mountainside, except it's made of glowing interstellar gas and dust. In Carina, massive stars like Eta Carinae and others are blasting the region with intense radiation, hollowing out vast cavities and leaving shimmering ridges. It's a stormy, active region of star birth, much larger and more chaotic than Orion's nursery. And there are so many more of these cosmic wonders scattered across the sky. The Lagoon Nebula in Sagittarius, for instance, is a vast, rosy cloud with a bright star cluster at its heart, easily visible in small telescopes on summer nights. The Trifid Nebula, not far from it, is a beautiful combination of an emission nebula and a reflection nebula, a single cloud glowing red in parts and reflecting blue in others, divided by dark dust lanes into a trilobed shape, hence its name Trifid. There's the Omega Nebula, sometimes called the Swan Nebula, which looks like a checkmark or a swimming swan in glowing gas, and the Rosette Nebula in Monoceros, an enormous circular cloud that truly resembles a flower in deep photographs. Each of these is a stellar nursery of varying size and activity, and each has its own unique appearance and story. Some are relatively peaceful homes to modest clusters, while others are blazingly lit by groups of massive stars. Together, they paint a picture of a galaxy continually abuzz with stellar creation. And yet, even Carina pales next to the mightiest stellar nursery in our local corner of the universe, the Tarantula Nebula. Now, the Tarantula Nebula isn't in our Milky Way. It's in a neighboring galaxy called the Large Magellanic Cloud, but it's worth mentioning because of its sheer scale and intensity. This nebula is an absolute giant, over 500 light-years across, and it's forming stars at a rate and size that dwarfs anything in our galaxy. It's so massive and bright that even though it's about 160,000 light-years away, under very dark skies, the Tarantula Nebula can be faintly seen with the unaided eye. It looks like a small cloud in the constellation Dorado. Inside this monstrous cloud, there are clusters containing hundreds of thousands of young stars. Some of those stars are among the most massive and luminous we know of, titans over 100 times the mass of our sun, shining millions of times brighter. These stellar Goliaths live fast and die young. They will blow themselves apart as supernovae after only a few million years, enriching the nebula further with heavy elements. The Tarantula Nebula is essentially a preview of what a starburst region looks like, a place where star formation is on overdrive. In fact, conditions in the Tarantula Nebula might resemble what was going on in the early universe on a smaller scale, or in interacting galaxies where huge swaths of gas collapse at once. It's a reminder of how powerful and vigorous star formation can become under the right circumstances. Not every galaxy has such extreme stellar nurseries, though. There are galaxies where star formation has calmed down. For example, large elliptical galaxies have used up or lost most of their gas, so they have very few new stars forming. Their nebulae are mostly from dying stars, not forming ones. On the flip side, there are starburst galaxies where interactions or mergers have lit up enormous nebulae all over, creating stars at a furious rate. For example, when two galaxies collide, like the antennae galaxies currently merging about 60 million light-years away, they kick off an extravagant burst of star formation. In the antennae, we see vast swathes of pinkish light, gigantic nebulae where tens of thousands of massive stars are forming nearly all at once. If you could stand on a hypothetical planet within one of those starburst regions, though it would be a very hostile environment for a planet, your night sky would be overwhelmed by the brilliance of nearby newborn star clusters. You might see dozens of intense blue-white suns lighting up the heavens, and every so often one might explode as a supernova, adding a sudden flash of light to the cosmic backdrop. Such a scene would be dazzling and chaotic compared to the relatively tranquil skies we enjoy on Earth. Starbursts don't last long, perhaps a few tens of millions of years, but they transform their galaxies while they rage, rapidly turning gas into stars and pouring energy into their surroundings. Our Milky Way is somewhere in between these extremes. It forms a few stars per year on average, steadily, but not spectacularly. That might sound modest, but over millions of years, it adds up to a vast population of new stars. And each of those stars, remember, might host planets. So the nurseries in our galaxy are not just giving us stars, but possibly new worlds by the thousands as well. Now, you might be asking, how do we actually know all this about nebulae and star formation, given that these things happen on timescales far beyond a human lifetime, and in places so distant we cannot visit? This is where the ingenuity of science and technology comes in. We've been fortunate to live in a time when human beings have built incredible telescopes and detectors to be our eyes and ears in the cosmos. It's taken centuries of curious minds piecing together the puzzle to get to our current understanding. Historically, nebulae puzzled astronomers for a long time. In the 1700s and 1800s, people like Charles Messier and William Herschel cataloged these faint smudges in the sky. Messier was actually hunting comets and kept a list of annoying fuzzy objects that are not comets. The Orion Nebula, for example, ended up as Messier 42 in his list. William Herschel, who discovered Uranus, also surveyed nebulae, and at first thought maybe they were just dense clusters of stars so far away that his telescope couldn't resolve them into individual points. For some nebulae, that was a reasonable guess. After all, the Andromeda Nebula did turn out to be not a cloud of gas, but a galaxy full of stars. But for others, like the Orion Nebula, no matter how good the telescope, there was clearly a luminous fog present, not just stars. The breakthrough came with the advent of spectroscopy, essentially splitting light into a rainbow spectrum to see the fingerprints of different elements. In 1864, an astronomer named Sir William Huggins, working with his wife Margaret, turned a spectroscope toward the Orion Nebula and some other bright nebulae. What he saw were bright emission lines at specific colors rather than a continuous rainbow. This was the telltale sign that the nebula was made of hot, glowing gas. Each chemical element gives off light at specific wavelengths when it's excited, and Huggins recognized the signature of hydrogen in the nebula's light. One line, however, was a mystery. A bright green line that didn't match any element known on Earth at the time. This baffled scientists, and they even hypothesized a new element, which they whimsically named Nebulium, to explain it. For decades, this remained a puzzle. It wasn't until the early 20th century that we figured out the truth, that green line came from ordinary oxygen atoms in conditions so rarefied, such low density, that they almost never occur on Earth. In the laboratory, such a transition had never been seen because our labs couldn't reproduce the extreme thinness and isolation of atoms in a nebula. In the deep vacuum of space, an excited oxygen atom can hang out for minutes before emitting that green photon, something impossible in the crowded conditions on Earth. So, there was no nebulium, just well-known elements behaving in exotic ways in the deep quiet of interstellar space. Huggins' work was the first big confirmation that nebulae were made of gas. As photography improved, astronomers began capturing images of nebulae that revealed more than the eye could see. On September 30th, 1880, an astronomer named Henry Draper took the first ever photograph of the Orion Nebula using an 11-inch telescope and an exposure of 51 minutes. The black and white image was grainy by today's standards, but it showed the glow of the nebula and hinted at its wispy structure. A few years later, in 1883, another astronomer, Andrew Ainslie Common, took longer exposures up to an hour that revealed even more. The Orion Nebula was far more extensive than what you could glimpse through a telescope by eye. Photography was opening up the true complexity of nebulae. By the early 1900s, better photos showed that nebulae often had intricate structures, tendrils, shells, rings, suggesting dynamic processes at work. Another breakthrough came when those photographs and later observations showed that some nebulae were changing over time, expanding, in fact. On a summer night in the year 1054 AD, Chinese astronomers documented a sudden new star appearing near the constellation Taurus. It was so bright it rivaled the moon and remained visible even in daylight for weeks. The people of that time could not have known what they were witnessing. A massive star ending its life in a catastrophic supernova. That brilliant guest star, as they called it, eventually faded and vanished from the sky, recorded in a few chronicles and then largely forgotten. Nearly 1,000 years later, modern astronomers turned their telescopes to a curious glowing cloud, now known as the Crab Nebula, in that same part of the sky. They realized it was the expanding debris of that very explosion from 1054. The nebula, with its tangle of filamentary structure and eerie bluish glow due to a rapidly spinning neutron star at its center, is essentially the corpse of a star, a stellar nursery in reverse, so to speak, where instead of a cloud contracting to form a star has exploded and left an ever-expanding cloud. The Crab Nebula grows outward at thousands of kilometers per second. By comparing photographs taken years apart, Astronomers in the early 20th century could actually see its filaments moving. It was a stunning confirmation that some nebulae are the aftermath of stellar death, and it reminds us that nebulae mark both the beginnings and the ends of stars. In the 1920s, the big debate in astronomy was about the nature of the so-called spiral nebulae, fuzzy spiral-shaped objects seen in the sky. Some astronomers, like Harlow Shapley, argued these were part of our Milky Way, perhaps swirling gas clouds or clusters, while others, like Heber Curtis, suspected they were entire island universes, other galaxies outside our own. The matter was dramatically settled when Edwin Hubble, the man, not the telescope, although it's named after him, observed variable stars in the Andromeda Nebula and proved it was far outside our galaxy. The Andromeda Nebula became the Andromeda Galaxy, and suddenly the universe got a lot bigger. After that, the term nebula was reserved mostly for gas clouds within our galaxy, and by extension within others, while those spiral nebulae were recognized as separate galaxies full of their own stars. This realization also put our study of nebulae into a new context. These glowing clouds were not everywhere, but specifically in galaxies, typically in their spiral arms, as we discussed. Through the 20th century, our tools kept improving. We built bigger telescopes on higher mountains, launched telescopes into space, and developed detectors that could see light beyond the visible range, like radio waves, infrared, ultraviolet, and X-rays. Each of these new windows showed us something new about nebulae. In 1990, NASA launched the Hubble Space Telescope into orbit above the blurring effects of Earth's atmosphere. After a tricky start, they famously had to fix its mirror's slight flaw with a space shuttle mission. Hubble began sending back images of clarity and depth that had never been seen before. Nebulae, which had appeared as ghostly smudges in earlier photos, now blossomed into landscapes of astonishing detail. Those famous images you might have seen, like the pillars of creation in the Eagle Nebula or the Carina Nebula's towering clouds, were taken by Hubble in the 1990s and 2000s. They stunned not just astronomers but the whole world with their beauty. But beyond beauty, they provided scientific insights. For instance, in the Orion Nebula, Hubble was able to resolve hundreds of small dark disks surrounding young stars, exactly those protoplanetary disks we expected to see. It confirmed that many, perhaps most, newborn stars have the raw material for planetary systems around them. Hubble identified more than 150 of these proplyds, short for protoplanetary disks, in Orion, appearing as little silhouetted ovals or circles against the nebular glow. These are essentially solar systems in the making. It was an affirming moment. We weren't just theorizing that stars have disks. We were actually seeing them. If someone ever asks how we know other stars have planets, one answer is that we literally observed the birthplaces of those planets in places like Orion. Hubble also gave us time-lapse clues in nebulae. By taking images of the same nebula years apart, astronomers could see subtle changes. For example, in the aforementioned Crab Nebula, the supernova remnant, Hubble images show the eerie filaments moving outward over the span of a few years. In the Helix Nebula, a closer planetary nebula that looks like a big eye in space, Hubble revealed comet-like knots of dust and gas on the edges, possibly being shaped by the dying star's last breaths. These details enriched our understanding of the dynamics in nebulae. But visible light is only part of the story. Many regions in nebulae are shrouded in dust that visible light can't penetrate. Young stars, before they emerge, are hidden deep inside. To truly peer into the womb of the nebula, astronomers use infrared telescopes, since infrared light can travel through dust more readily. The Spitzer Space Telescope, launched in 2003, and more recently, the James Webb Space Telescope, launched in 2021, have given us that capability. Spitzer, for example, could see the heat glow of embryonic stars inside dark pillars and clouds. It produced a famous image of the Swan Nebula's center, showing dozens of newborn stars that were invisible in earlier photographs. James Webb, being much more powerful and with higher resolution, took this further. In 2022, one of Webb's first images was of the cosmic cliffs in the Carina Nebula. In Webb's infrared vision, the scene looks different from Hubble's version. The dust is more transparent, and suddenly you see many more reddish stars sprinkled throughout the cloud. Those are baby stars still wrapped in their nurseries, some so young they haven't blown the gas away yet. Webb essentially allowed us to peer inside the nursery, witnessing stars at the earliest stages of formation that are completely invisible in visible light. It's like having X-ray vision to see the babies inside the womb of the nebula. Then there's radio astronomy, facilities like the ALMA array in Chile, which detect the faint radio waves emitted by cold gas and molecules in space. One of ALMA's most striking achievements was capturing images of protoplanetary disks around young stars. In one famous observation, ALMA revealed the disk around a newborn star called HL Tau in unprecedented detail, showing a series of concentric bright and dark rings. Those rings are essentially the footprints of planets forming and carving gaps in the disk. It was direct evidence of planet formation in progress, like seeing the grooves in a record being cut as the music plays. For the first time, we could literally see the likely locations of developing planets embedded in a nebula's leftover material. It was a jaw-dropping confirmation that the processes we long theorized were really happening. New worlds assembling in the dust around a young star, right there in the data. Through radio observations, scientists also map the presence of various molecules in these clouds. Much of the gas in star-forming regions is molecular hydrogen, H2, which doesn't emit radio waves we can easily detect, but it can be traced by a proxy molecule, carbon monoxide, CO, which does emit in radio frequencies. By mapping CO emission, ALMA, and other radio telescopes outline the structure of cold molecular clouds, even the parts too dark to see in visible light. Radio astronomy has also unveiled a rich chemistry in nebulae. These clouds turn out to be cosmic chemistry labs, where all sorts of molecules form. We have found simple organic compounds like formaldehyde and methanol, alcohols, ethers, and even sugars like glycolaldehyde, and ingredients for amino acids, all drifting in these stellar nurseries. On the surfaces of dust grains in the coldest parts of the clouds, atoms meet and react, building more complex molecules. It's amazing to think that the building blocks of life, organic molecules, are cooking in these nebulae long before there are planets for them to possibly seed. Studies of meteorites and comets in our own solar system show they contain a menagerie of organic compounds that must have formed in the natal cloud that gave birth to the sun and planets. So, star nurseries aren't just forging stars. They're preloading the environments of future planets with the raw ingredients of life. And indeed, astronomers have detected plenty of water in star-forming regions too, often in the form of water ice on dust grains or water vapor in the gas. That means many new planets may start out with a supply of water, a promising sign for eventual habitability. With each technological leap, better telescopes, new wavelengths, more sensitive instruments, we've peeled back another layer of the nebulae. we've gone from fuzzy patches to understanding that inside those patches are worlds in the making, stars in infancy, and even the echoes of stars that died. And yet, there's still so much we don't fully grasp. Star formation is an ongoing research frontier. Astrophysicists run complex computer simulations to try to recreate a nebula giving birth to stars, but the process is chaotic. Turbulence, magnetic fields, rotation, and feedback from young stars all interplay in complicated ways. Questions remain, like, what exactly determines how many stars a cloud will form and of what masses? We do notice a pattern in how stars are born. Star formation tends to produce many more small stars than very large ones. For every blazing O-type giant that a nebula makes, there will be dozens of sun-like stars and perhaps hundreds of even smaller red dwarf stars. This seems to be a universal trend. Astronomers call it the initial mass function. But we don't yet fully understand why nature prefers to form lots of small stars for each handful of massive ones. It likely has to do with how the cloud breaks up. Perhaps turbulence shatters the cloud into many little pieces, or maybe the physics of cooling gas favors the formation of more low-mass clumps. Whatever the cause, the outcome is that long-lived, modest stars like our Sun and smaller are abundant, while the short-lived heavyweights are relatively rare. If it were the opposite, the galaxy would be a far more violent place. This comforting imbalance is something we observe, but still strive to explain in detail. Why do most stars form in groups? How exactly do planets manage to form in the midst of all this chaos and intense radiation? And what about the very first stars that formed when the universe was young? How did those differ? The first generation of stars in the universe, often called population 3 stars by astronomers, likely formed within just a few 100 million years after the Big Bang, when there were not yet any of the heavy elements, metals in astronomer lingo, that we find in later nebulae. Those primordial nebulae were made of pure hydrogen and helium. Without elements like carbon, oxygen, or dust grains to help the gas cool and fragment, theory suggests the first stars might have grown to be extremely massive, much larger than most stars today. They would have burned hot and blue, lived for only a short time, a few million years or less, and then died in titanic supernova explosions. In doing so, they seeded their surroundings with the very first heavy elements: carbon, silicon, iron, and so on. Those enriched materials then mixed into new nebulae, enabling the next generations of stars to form in the more familiar patterns we see now, with plenty of smaller stars among them. In a way, the universe had to go through an initial phase of giant stars to manufacture the ingredients needed for things like planets and people. Capturing the light from those first stellar nurseries is extremely challenging. They are very distant and faint now. But telescopes like James Webb are peering deeper into space, and thus further back in time, than ever, searching for telltale signs of those earliest star-forming clouds in the young universe. The more we learn, the more we appreciate that nebulae are not just static clouds, but dynamic, evolving objects. A stellar nursery can be born, flourish for a while, and then disperse, a bit like a dandelion puff being blown apart. A supernova might go off nearby and trigger new spots of star formation, even as it destroys others. In some nebulae, like Carina, as we mentioned, we see possible chain reactions. One generation of stars, especially the big ones, can affect the next. Perhaps a star that formed 1 or 2 million years ago in a corner of the cloud goes supernova, and its shockwave compresses another part of the cloud, leading to a new cluster of stars forming there, a sequential propagation of star birth. Nebulae are scenes of both creation and destruction, intertwined. Considering future possibilities, who knows what we might witness as technology advances further? We might build telescopes that can watch the same region of a nebula over decades and start to catch subtle changes, like a protostar getting brighter as it accretes a new chunk of mass, or gaps forming in a disk as a planet emerges. We might develop instruments to measure the winds in nebulae directly, or to detect the glow of forming planets still embedded in the gas. Perhaps we'll even send probes or robotic telescopes much closer to some of these regions one day. Although even the nearest star nurseries are still incredibly far for space travel, hundreds of light years, so that's a far future dream. But imagine a robotic probe sent into the Orion Nebula, taking close-up pictures of protoplanetary disks and sniffing the local chemistry. It sounds like science fiction now, but so did landing robots on Mars once. Even without leaving Earth, our capabilities are growing. The upcoming generation of extremely large telescopes, with mirrors 30 meters across and more on the ground, will be able to resolve individual stars in distant nurseries and perhaps even young planets in the act of forming. We're also honing techniques to detect the vibrations in newborn stars, astroseismology, to learn about their internal structure, and to measure the magnetic fields threading through nebulae to understand their role in star birth. All these insights make nebulae not just abstract, distant things, but places that are intimately connected to the story of existence. They are the wombs where stars, and by extension, planetary systems, and everything on them, begin. Because of that, nebulae tie together the life cycles of nearly everything in the universe. A nebula can be thought of as a chapter in a great cosmic story. In one chapter, the nebula is the beginning, the nursery. And in another chapter, a nebula is the end, the graveyard, like the Crab Nebula or the Ghostly Veil Nebula from an exploded star. One stage's end is another stage's beginning. Our own existence traces back through this chain. If you follow it, humans to Earth, Earth to the Sun, Sun to the solar nebula that bore it, that nebula to earlier stars that died and enriched it. And those earlier stars? They came from nebulae before them, which in turn were seeded by even older stars, and so on, back to the first stars. It's a continuity that spans billions of years. Now, for a moment, let's embark on a brief imaginative journey through some of the stellar nurseries we've talked about, and maybe a few we haven't yet. Picture yourself in a ship capable of hopping across light years at will, touring the highlights of our galaxy's star-forming realms. Our first stop, the Orion Nebula itself. You disengage your faster-than-light drive and suddenly find yourself hovering in a region of space aglow with a soft, ethereal light. All around, a faint haze of pink and purple surrounds you, the diffuse glow of hydrogen gas energized by young stars. Ahead, you see the heart of the nebula, the trapezium cluster, 4 fiercely bright stars grouped in a tiny area, shining like a cluster of diamonds on black velvet. They illuminate enormous swirls of gas that billow out around you. If you tilt your ship's orientation, you might catch sight of dark, globular silhouettes, denser clumps and disks around fledgling stars, appearing as little round shadows against the nebular light. Being here feels serene and humbling. The nebula is quiet on human timescales, yet you know it's a place of furious activity over thousands of years. It's as if you are standing in a silent nursery at night, aware that come morning, this place will be bustling with new life. With a gentle command, you engage the engines and leap across light years to the next destination, the Eagle Nebula. Dropping out of hyperspace, a breathtaking scene greets you. 3 giant towers of gas, the pillars of creation, rise from a glowing cloud base like ghostly mountains in space. They have a brownish golden hue against the emerald and blue backdrop of ionized gas, colors that, if your eyes were sensitive to infrared and visible combined, you might perceive. You navigate your ship around one pillar, and it looms for light years above, a cathedral of star stuff. Within these towers, new stars are gestating, hidden in pockets of density. Near the tips of the pillars, the relentless light from a cluster of massive newborn stars, just off to one side, above the pillars, is eating away at the columns, casting their outlines into sharp relief. It's a scene of sublime beauty, tranquil to your immediate senses, yet fundamentally an epic battle between starlight and cloud. You feel a pang of poignancy, knowing that these structures, as monumental as they are now, are temporary. They are being sculpted and eroded, even as you admire them. Eventually, the pillars will dissolve, unveiling the stars forming inside. Next, you set course for the Carina Nebula, jumping thousands of light years farther. This region appears even more expansive. A vast panorama of bright and dark patches sprawls before you, filling your view. Here, the gas forms a kind of landscape, great walls and canyons of cosmic material. One such feature is the cosmic cliffs, a gigantic, craggy ridge of gas and dust that stretches for dozens of light years, glowing at its edges where newborn stars on the other side light it up. You fly parallel to this ridge, marveling at the gradation of colors. The base of the nebula glows with a deep orange-red, ionized sulfur, blending into zones of green, hydrogen, and blue oxygen higher up, a pastel sunset in space carved by stellar winds. Speckled throughout are stars at various stages of life. Some are embedded deep in the nebula, visible only as faint reddish embers, their light dimmed to red by dust, while others are out in the open, blazing white-blue and casting stark rays of light and shadow through the gaps. Off to your side, you spot a particularly brilliant star with a bluish-white hue. That must be Eta Carinae, the erratic giant of this region. Even from a safe distance, it's almost blinding, and your ship's sensors automatically dim the view to protect your eyes. You recall how this star erupted in the 19th century, and you feel a shiver realizing that it could explode for real at any time in the future. The Carina Nebula feels alive with energy, larger, more wild than Orion's cozy nook. It's as if the calm nursery has grown into a bustling city of starbirth, complete with cosmic skyscrapers and storms. Finally, for a truly grand spectacle, you hop over to the Tarantula Nebula in the large Magellanic Cloud, outside the Milky Way. As your ship arrives and you drop out of faster-than-light travel, you're momentarily speechless. The scale of this nebula is overwhelming. It fills your view like a vast web of nebulosity, befitting its spider-inspired name. Everywhere you look, there are clusters of stars, not just a handful, but countless stars in massive groupings that dot the nebula like towns in a glowing countryside. The light from so many stars makes the surrounding gas cloud fluoresce intensely. The Tarantula Nebula has a core region where the density of stars is almost like a globular cluster of newborns. This is the R136 cluster, home to some of the most massive stars on record. They shine with a fierce white-blue light, so powerful that even from many dozens of light years away, you have to put up filters to dampen the glare. You navigate through filaments of gas, stretching outward from the core, like the legs of a cosmic spider. Some filaments are being propelled by shock waves from recent supernovae. Yes, here stars are dying nearly as often as they're born. In fact, as you watch, You imagine one of those monster stars reaching the end of its short life and detonating, adding a fresh, expanding nebula to the mix. The Tarantula Nebula is an extreme environment. It's as if you've stepped into a much younger version of the universe, where everything is bigger and happening faster. After soaking in this awe-inspiring vista, chaotic, radiant, and teeming with raw power, you prepare to return home, carrying with you a profound appreciation of how diverse and magnificent stellar nurseries can be. Now, you might be asking, how do we know all this? And how can we be so confident in our understanding of these distant places? As we've discussed, it's the culmination of decades, and really centuries, of astronomical observations across all sorts of light, from visible to infrared to radio, combined with physics. We use the laws of nature, tested in laboratories and closer to home, to decode what we see in those lights and spectra. Every observation, whether it's a spectrum showing a particular chemical fingerprint or an image revealing a certain structure, feeds into our cosmic story. We also continually test our theories by simulating conditions with computer models and seeing if they produce structures like the ones observed. It's a bit like meteorologists modeling a storm system, except these storms last 100,000 years and span trillions of kilometers. While there are aspects we know well, like the basics of gravity and heat, the devil is in the details, and those details keep researchers busy. But with each new telescope and each ingenious observation, our picture gets sharper. One pattern that has emerged is how connected everything is. Nebulae are not isolated entities doing their own thing independently. They are part of the galactic ecosystem. For instance, when a cluster of stars disperses and its nebula is blown away, that gas doesn't just disappear. It becomes part of the general interstellar medium, often forming or joining other clouds. Some might eventually fall toward the galactic center. Some might get swept into new spiral arm density waves, and in time, collect into a new nebula elsewhere. The galaxy is recycling its materials over and over. The calcium in your bones might once have been in the gas around some long-dead star, then in a nebula, then in another star, then in a nebula again, before finding its way into Earth. Think about that for a moment. The atoms in your body have likely seen multiple nebulae and star cores in their history across billions of years. We live in a relatively quiet part of the galaxy right now, which is good for us. Too close to a big nebula, and the intense radiation might be harmful. The sun is currently passing through an area called the local bubble, a region of low-density hot gas, likely blown by ancient supernovae. This bubble is kind of like a cavity in the galactic arm, but not far, astronomically speaking, are some molecular clouds, like the Taurus molecular cloud, about 450 light-years away, where stars are forming quietly, or the Rho Ophiuchi cloud we mentioned. So even near us, the cycle continues. As our journey tonight comes to a close, let's take a step back and reflect on what we've explored. We started from the simple question of how a star can come from a cloud. We wandered through dark, quiet nebulae and saw how gravity can sculpt them into new suns. We imagined diving into these clouds, seeing cosmic dawns from within. We traveled across the galaxy and even beyond, witnessing the panorama of stellar nurseries large and small. We learned that these beautiful clouds are the crucibles of creation, and that we carry pieces of them within us. Isn't it comforting, in a cosmic sense, to know that out of darkness and diffuse gas, light and life can emerge? That from something as intangible as a nebula, so faint and ghostly, can come the warmth of a sun, the stability of a solar system, maybe even the spark of life on a new world. There's great hope and poetry in that realization. Nebulae show us that even in the cold vacuum of space, when the conditions align, creation happens. They are a testament to the universe's ability to organize chaos into something as brilliant as a star or as precious as a living planet. Take a deep breath now and imagine that gentle glow of a nebula out there in the darkness. It's peaceful and vast. The same laws of nature that cause that nebula to form stars are at work everywhere, even here in the air you just breathed. The oxygen in it was forged in a star long ago. We are connected to these distant clouds through the very substance of our bodies. In a sense, we are children of the nebulae. As we wind down, let your mind drift among the stars for a moment. Think of the stellar nursery that gave birth to our sun. Long gone now, but once it was as real as Orion's nebula. Think of the star-forming regions we cannot yet see in distant galaxies billions of light years away, where perhaps new stars, and maybe new civilizations eventually, are coming to be. The universe is continually renewing itself, and nebulae are the hearths of that renewal. Thank you for joining me on this long but wondrous journey through the star nurseries of the cosmos. I hope it has brought you both fascinating insights and a calming sense of connection to the bigger picture. As you close your eyes, picture those serene cosmic clouds hanging in the starlight, nurturing new suns that will one day shine. Sleep well, and may your dreams be filled with the wonder of nebulae and the stars they bring forth. Good night and pleasant dreams.